Okay, so the fourth and final experiment with the air track is to show the relation between F and A. F is equal to ma. So we have exactly the same apparatus as you can see for acceleration, and we know we can measure the acceleration each time, and we can measure the applied force each time by either getting the weight of the slotted weights and pan on a balance, or just reading them off what's been given. Okay, so effectively this is the formula we're trying to show. So we want to show the relation between F and A. So the easy way of doing it is say F is equal to ma. So we put F on the y-axis, A on the x-axis, and the slope becomes m. So that's pretty much the straightforward way of doing it. If you want to be more elegant, you say, okay, I'm changing the force. That's what should be on the x-axis. So you put that on the x-axis, put A on the y-axis. So you're now using this form. A is 1 over m times F. F is equal to ma, like that. Okay, if you come back up to here, okay, then the slope is 1 over m. Remember, in general, it's worth noting that if you change the axes, if you swap the axes, the slope becomes its reciprocal. So m mass, it becomes 1 over mass. Okay, always. So in this case, it's interesting. I think in general we'll use a simple one. Okay, so the problem here is we can have two variables. The first variable is the weight, which is the weight of the pan plus contents. The second variable is the acceleration, which we can measure, as we did in the last experiment, using the card and the light gates. Okay? The third thing that can be a variable is the mass that's being accelerated. And don't fall into the trap. The mass that's being accelerated is not just the rider and card, it's also the string, and it's also actually the pan and contents. So that has to be kept constant. Now, how do we keep that constant if we have to increase the force? So we have to get a weight and add it to this. Okay, so we have a problem, because then we're increasing the force, but we're also increasing the mass. So to get around that, what we do is we take all the weights at the beginning, okay, and we put them on the pan. Okay, so think about it now. Okay, probably have to put another one in if we were doing it. Okay, you have 4 weights there, and you also have the weight of the pen. So when we do this the first time, okay, right, the force is going to be just the weight of the pan. The mass will be the mass of the pan plus the mass of the string plus the mass of the rider plus the mass of the card plus the mass of the extra weights. When we've done it the first time and we're done, we then take a weight from here. We put it over here. Now, let's think about it. Have we increased the force? We have. The force is now bigger because we've added a mass. Okay? The acceleration will obviously change. We want the mass to stay the same. Is the mass that's being accelerated the same? Well, it is, because all we've done is we've moved the mass from here to here, but the total mass of the pan and contents and the string and the rider and the weights that haven't been moved yet and the card is the same. So that's how you make sure that you only have 2 variables. That's the subtle bit. That's what you have to watch. We just repeat this experiment about 5 or 6 times. For each of those, we get the force, which is the weight of the pan plus contents, the acceleration, as we did in the previous experiment, by getting the initial velocity and final velocity and displacement each time, and then we draw a graph of F against A. We get a straight line through the origin, showing that F is proportional to A, and therefore that gives us the relationship. Okay, that's it.